Okay, so this is a follow-up video to the last one where we're talking about a hydration of an alkene, which we noted gave a Markovnikov addition of water into the alkene pi bond, but because it went through carbocations was somewhat problematic due to rearrangements. So what we're going to be talking about today is two alternative methods. One is this one, which is known as oxymercuration demercuration, which states that when you take an alkene and you treat it with mercury 2 compounds, compounds that contain mercury 2 ions in the presence of water, followed by sodium borohydride reduction. That's a reducing agent that is used for these types of reactions. And just to mention, when we talk about reduction in organic chemistry, we're generally talking about the addition of hydrogen with electrons, basically a hydride addition into a system. The net result, of course, is gaining of electrons, which is why it is a reduction. Nevertheless, you'll get more into that in organic too. But what the end result is that you get a Markovnikov addition of water into the alkene with no rearrangement. So if you were to look at the compound that we were considering last time, which was this alkene, we noticed that if you just did your typical hydration, that you end up with a methyl shift occurring and a rearranged product and not getting the desired alcohol. Well, in this particular case, if you were to treat this alkene with some source of mercury 2, so I'm going to use mercuric chloride in the presence of water. And typically these are run in polar aprotic solvent. Just to help with solubility, this is acetonitrile. And then followed by sodium borohydride reduction in the presence of hydroxide. That will lead to the formation of our desired alcohol. Now, of course, that is a racemic mixture, but nevertheless, the regiochemistry is correct here, where you've got the alcohol essentially having Markovnikov addition of water. Now, the way that this is able to work is the mercury adds in to the pi bond in a very similar manner to how halogens were adding into pi bonds, and so you end up with a marconium ion. Okay, and I'm only going to draw one of these out, but technically there is another one where the mercury's on the bottom face, and that's why you end up with a racemic mixture, but you end up with this species. Now, just like with addition of water, okay, into rhomonium ion, this is the same thing with these types of merconium ions. The water is going to want to add into the more substituted position because that's where the partial positive charge will be more stabilized. So the water ends up adding in there and opening up that merconium ion. Okay, so that's it for step one. Now, in step two, you'll notice that we're in base and a sodium borohydride. Well, what the hydroxide is in there for is to effectively remove that acidic hydrogen. And the role of the sodium borohydride is the sodium borohydride will transfer one of its hydrogens, electrons and all, into the carbon that's attached to the mercury and effectively kick the mercury out. And so that ends up adding a hydrogen here at this position. So that is how oxymercuration, demercuration is able to do this. Now, the net result of this is our regiochemistry, or regioselectivity for oxymercuration, demercuration, is you have a Markovnikov addition of water with no rearrangements. And your stereoselectivity is you end up with a racemic mixture if you produce a, well, I shouldn't say a racemic mixture, because if there's a stereocenter in there, it's not. It'll be a mixture of distereomers, so let's say racemization. Okay, so really, you're not getting any selectivity for one stereoisomer or the other. But there is a huge problem with this entire process, and that problem is that this is extremely toxic reaction. Organomercuries are very, very deadly, and so this reaction is one that is somewhat problematic, okay, because of that. Now, the other thing to note here is if you wanted to do this reaction, but you wanted to get the anti-Markovnikov product, you can actually do that with another set of reagents to accomplish this. So what if we wanted the anti-Markovnikov product? Okay. Well, then we're going to want to consider this method, which is hydroboration oxidation. Now, hydroboration oxidation is essentially when an alkene is treated with BH3, antipolar aprotic solvent, something like tetrahydrofuran, followed by an oxidizing agent in basic hydroxide. And you end up with essentially adding water in an anti-Markovnikov manner. So just to give you an overview of this, this is a molecule BH3 in the presence of THF, and then followed by peroxide in base. You would see this is the major product now, where the alcohol has added on the carbon on the right, and you can see we've added hydrogen to the carbon that has the fewest number of hydrogens. Okay. Now, mechanistically, the way I'm going to do this is I'm going to use a little bit smaller molecule to kind of explain how this is working. It's the same idea. So if you were to do this reaction, let's say with this alkene, the first thing that's important to note here is that you need three equivalents of your alkene when it reacts with your BH3. And the reason is because the first intermediate that you produce before you oxidize it is this trialkyl borane. Now, how that ends up coming about is your pi electrons are attracted to the BH3. And the way they're attracted to them, so this is carbon 1, this is carbon 2, this is carbon 1, this is carbon 2, is that when it adds the boron and the hydrogen in, it does so with a particular regioselectivity, meaning that it adds it on the same face of the alkene, but it also adds it in a way so that the boron is attached to the carbon that's less substituted, and that is really just due to sterics. So there's less sterics in the species. And notice here that as this addition is occurring, this is occurring with a syn addition when this happens. So the first thing that you end up with is, in fact, you end up adding hydrogen and the boron in this manner. And since there are 2 more hydrogens here in this particular species, this can react 2 more times. So you end up with 1, 2, 3 carbons, 1, 2, 3 carbons being bonded to the boron. Okay, so that's why you only need 1 BH3 for every 3 equivalents of your alkene. Now, once this has done that, well, now you're ready for the second part, which is the oxidation. And what this does initially, when you add in peroxide into this, is the boron ends up reacting with the peroxide, and it ends up rearranging into this species here. Now, you don't have to worry about the mechanism for that. I just wanted to show you what that particular intermediate looks like so that you can say you've seen it. But essentially, this is going to be a type of rearrangement where the oxygen adds into the boron and then the alkyl groups add on to those oxygens. This species is essentially reacts with the base, and then that starts to kick out alkoxides. So you end up with 3 alkoxides that are produced, and an equivalent of boric acid. Now, these guys are going to be able to deprotonate water that's in that system. And so you end up with 3 equivalents of your alcohol. Now, the mechanism for the oxidation is not really the one that I want you to be focused on. I'm more interested in that you understand this mechanism here for the for how this syn addition works initially when you add the boron into the system, because that's going to be the one that's important for understanding why you get the types of stereochemistry that you get. Try to zoom this back up a little bit. Okay. So, for example, if we had, let's say, this cyclic system, okay, so we had 1-methyl cyclopentene, and we did reaction with BH3, THF, followed by peroxide and base. Well, there's two possibilities here that could happen. So one possibility is if we draw this out, is that you could have addition that occurs on either the top or the bottom face. And so, meaning that if it was to come in from the bottom, if it was to come in from the bottom face, and again, this is a tertiary substituted alkene, this is the secondary one, so you would expect the hydrogen to be here and the boron to be here. Or if it were to attack, let's say, from the top face, this is the bottom, this would be the top. In other words, now hydrogen here, boron here, that's secondary, that's tertiary, that's secondary. So again, hydrogen still adding here on the more substituted carbon. But that's going to lead to two different products. So one where you have the hydrogen here underneath the CH3. Again, on the same face where you added the hydrogen, that's where the BH2 would be. Or where it adds from the top. And I'm just drawing in this hydrogen that was already here. There was already a hydrogen here as well. So you're ending up with those types of species. Now, one of the things I should have said, and this isn't terribly important, to concern yourselves with, but sometimes you need to use, it's not just a 1-to-3 ratio. Sometimes you do need more BH3 for the reaction to occur, especially if the molecule that you're adding the alkene is a very big, so there's going to be a lot of sterics associated with it. So oftentimes you need to add more BH3 in order to get it to react. That's not, such a major concern. What's more important is what your stereochemistry ends up being when this is all over. So what ends up happening when you do your oxidation part is you effectively replace where the boron is with the oxygen and the hydrogen, okay, when you do the oxidation. And so that stereochemistry is effectively retained. So you end up with this compound here, okay? Likewise over here on this side. If you were to replace the BH2 with an OH, you would end up with the OH here on this side. Now what I want you to do is to notice, if you look at these two compounds here, okay, what you should clearly see is that if you were to rotate this around, it would be the mirror image of this compound. And so this is a set of enantiomers that we have made from this reaction. And if you can't see it, I'm going to draw it out with just the wedges. So the OH group is down here and the methyl group is up here. And then on this side, the OH group is up and the methyl group is pointing back away. So I think now you should be able to clearly see that, okay? Now, one other thing to mention about this is that it is possible for alkynes to undergo these processes as well, okay? And I will just briefly mention this. So what about alkynes? So if you were to add acid with water, it would do a standard Markovnikov addition. So you would end up adding hydrogen to the side of the triple bond that has more hydrogens, which in this case would be the terminal end. And again, there is that enol species that we mentioned previously, which undergoes a rearrangement to a ketone. Likewise, if you were to do this reaction with oxymercuration, demercuration, you would see the same thing. And if you were to do the addition with hydroboration, oxidation, that you would end up seeing now the addition would be an anti-Markovnikov addition, so you would add hydrogen to the side of the triple bond that had the fewest hydrogens, which would be the one on the right side. And so the OH would go on the other side. Here we have an enol, and that will also undergo rearrangement, effectively converting the alcohol now into a carbonyl. Giving you this aldehyde, okay? right, so there was a lot of things that were talked about here in this particular section. There's a lot of rather complex mechanisms. I don't want you to get too hung up on those, particularly the reductions and oxidations, which are a little bit fuzzy at the moment. More important is the regiochemistry aspects, the syn addition and the stereochemistry that is produced from the hydroboration, and then the regiochemistry that's associated with the oxymercuration, demercuration. Okay, so what we're going to be doing in the next video is we're going to be talking a lot more about oxidative methods, okay, so ways to add actually multiple oxygens into alkene systems, and there's going to be a lot of useful chemistry, so I think I'm just going to have one video dedicated to that, and then we are almost finished at that point. So once we get to the oxidative methods, I've got one more addition reaction, and then we're going to review some reactions from this chapter, and then we'll be moving into spectroscopy. Okay, so I hope everybody's doing okay, and I will talk to you guys again soon. Take care.